Welcome back. Let's learn about unit vectors. Alright, so to start off, we're going to recall something from the previous lesson. I mentioned this very briefly, but didn't expand upon it because I'm going to expand upon it now in this lesson. And what I'm talking about is that if we have a vector and the magnitude or the length of that vector is 1, then we refer to that vector as a unit vector. But when we work with unit vectors, we're going to use a special notation to differentiate unit vectors from just a regular position vector. Instead of using the standard vector notation where we have this half arrow above our letter that represents a vector, we're going to use a different notation that looks like this. We'll have our vector, and then we're going to give it a little hat, or sometimes you'll hear this called a caret. Okay, but when you see this hat above a letter, and we're working with vectors, that means that that is a unit vector. Okay, but now throughout this video, to easily differentiate between our regular vectors and our unit vectors, I'm going to represent our unit vectors with a different letter. I'm going to write it like this. We'll have a vector u that is a unit vector. So this is how I'm going to refer to unit vectors primarily throughout this lesson, so just keep that in mind. Okay, but now let's actually start looking at some of the uses of unit vectors and how we can find them. And the first thing that we're going to look at is how to find a unit vector for any given position vector. Okay, so if we want to find a unit vector in the same direction of a particular vector v that is not a unit vector, all we have to do is divide that vector by its length or magnitude. All right, and that looks like this. The unit vector u that is in the same direction as vector v will be equal to vector v divided by its magnitude, which is equal to 1 divided by the magnitude times vector v. This is scalar multiplication right here. 1 divided by the magnitude of the vector is a scalar quantity that we're multiplying by vector v. Okay, so given a position vector v, all we have to do to find its corresponding unit vector is divide it by its own magnitude. All right, and so by doing that, the resulting unit vector will have a magnitude of 1. And so let's see if that holds true. Let's look at an example problem here. For this example, we're going to look at this position vector. Vector v is equal to 3, 4. This is the position vector of the point 3, 4. If we want to find the unit vector that corresponds to this vector, in other words, we're finding the unit vector in the same direction as v, all we have to do is find the magnitude of this vector and then divide it by that magnitude. Okay, so let's start by just finding the magnitude. The magnitude of vector v here is going to be equal to the square root of the sum of the components squared. So we'll have 3 squared plus 4 squared. So now if we simplify, this will be equal to the square root of 9 plus 16, right? 3 squared is 9, 4 squared is 16. 9 plus 16 is 25, so we have the square root of 25. I'll write that down. And we know that the square root of 25 is 5. So we know that the magnitude of vector v is 5. And so if we want to find a unit vector in the same direction of v, all we have to do is divide this vector by 5. So here's what that will look like. Our unit vector will be equal to vector v divided by 5. All right, or another way to write that would be 1/5 times vector v. And vector v, we know, is this vector right here. So I'm actually going to replace that. I'm going to write it like this. We'll have 3, 4. And now if we perform this scalar multiplication, we'll multiply 1/5 by each of these components. 1/5 times 3 is 3/5. 1/5 times 4 is 4/5. So the resulting unit vector will be 3/5, 4/5. This will be the unit vector in the same direction of vector v that we started with. And so all that means is that this unit vector has the same direction as this position vector, except this vector has a magnitude of 1. It's a unit vector. And so let's see if that's true. If we look at the magnitude of our unit vector here, that will be equal to the square root of the sum of the components squared. So we'll have 3/5 squared plus 4/5 squared. And if we square those components, we'll have the square root of 3/5 squared 3 squared is 9, 5 squared is 25. So I'll have 9 25ths plus 4 fifths squared. 4 squared is 16, 5 squared is 25. So I'll have 16 divided by 25. And if we combine these fractions, they have the same denominator, so we can add the numerators. 9 plus 16 is 25. So we'll have 25 divided by 25, which is 1. So this is equal to the square root of 1, which of course is equal to 1. So the magnitude of our unit vector is 1, just like we know it should be. Okay, so this is our unit vector in the same direction of vector v, and we have now shown that it does have a magnitude of 1. Okay, and a quick side note, if you wanted to find a unit vector in the opposite direction of the position vector v, all you would have to do is add a negative sign to this calculation. If you negate the position vector and divide by its magnitude, that will give you the unit vector in the opposite direction of vector v. Okay, and the reason for that is simple. If you remember, when you perform scalar multiplication, multiplying by a negative scalar is going to reverse the direction of the vector. All right, so that's how you'd find a unit vector in the opposite direction of vector v. But I'm going to remove those negatives because this is the most common version of this formula that you will use. Typically, you want to find a unit vector in the same direction as vector v. Okay, and so I'm going to go over this one more time to summarize what we learned here. To find a unit vector in the same direction of a position vector v, simply just divide that vector by its own magnitude. Now, if we take a closer look at that formula that we just used, the unit vector is equal to 1 divided by the magnitude of v times vector v, what happens if we solve for this position vector v in this equation? Well, in order to do that, all we have to do is multiply both sides of the equation by the magnitude of vector v, and that will give us that vector v is equal to its own magnitude times the unit vector u. And this right here is a very important equation. What this tells us is that any position vector can be defined by a magnitude multiplied by a unit vector. All right, and this is an important realization because if you remember from the very first lesson on vectors, you learned that vectors are defined by a magnitude and a direction. And that's exactly what we have right here. This vector v is equal to its magnitude multiplied by a unit vector, which represents the direction, right? This unit vector is in the same direction of whatever this position vector will be. And so we have the magnitude and the direction of our vector right here. The vector is defined by its magnitude and direction. All right, so the two important takeaways here are that every position vector can be defined by magnitude multiplied by a unit vector. That's exactly what this is right here. And we also now know that unit vectors describe direction. Okay, so when you think about unit vectors, I want you to think about direction. Unit vectors are used to tell you the direction of your vector. All right, and that is very important going forward in Calculus 3, because now what we're going to look at are some special unit vectors that will allow us to define any other vector. All right, so next up, I'm going to introduce to you probably one of the most important concepts that you are going to use throughout all of Calculus 3. And that is the idea of standard unit vectors, or sometimes you'll hear them called standard basis vectors. And so in this video, we have two standard unit vectors that we're going to look at. There's actually a third one that you will use a lot later in Calculus 3 when we work in 3 dimensions, but right now we're still working within a 2-dimensional system, so we'll worry about the third one later. But what we have here are the standard unit vectors for the x direction and the y direction. All right, so for the x direction, we have the unit vector I, or sometimes you'll hear me call this I hat. And I hat is equal to the position vector of the point 1, 0. It represents a unit of 1 in the x direction. And you can see that in our graph here. This vector right here, that is vector I. It reaches out to the x value of 1, and that's it. It's just a vector that rides along the x-axis to that x value of 1, and it has a length of 1. And you can see that if you try to calculate the magnitude of this vector. I'll do that real quick. The magnitude of vector I, or I hat, is equal to the square root of the sum of the components squared. So we have 1 squared plus 0 squared. That's just equal to the square root of 1, which is 1. And so I is a unit vector. It has a magnitude of 1. Okay, so that's the standard unit vector in the x direction, but then we also have a standard unit vector in the y direction, and that is vector j, or j hat. J is the position vector of the point 0, 1. And so this vector represents a unit of 1 in the y direction. And so if you take a look at our graph here, this vector right here, that is vector j, or j hat, and it starts at the origin and reaches out to the point 0, 1, which means we have a vector along the y-axis with a magnitude of 1. All right, so this is a unit vector. Just like we checked the magnitude of vector I, let's quickly check the magnitude of vector j. The magnitude of vector j will be equal to the square root of the sum of the components squared. So we'll have 0 squared plus 1 squared, which once again is just the square root of 1, which is equal to 1. So just like I, j also has a magnitude of 1, so it is a unit vector. Vector I is the standard unit vector in the x direction, and vector j is the standard unit vector in the y direction. All right, so this is cool and all, but I bet you're probably wondering, what is the use of this? Why do we define these standard unit vectors? What are they good for? Why are they going to be so important for the rest of this course? Well, what these standard unit vectors will allow us to do is define the x and y directions of any position vector. We can use these two vectors to describe any other vector. And so let's take a look at that next. Okay, so if we have a position vector v and its components v1 and v2, notice that we could break up this vector into the combination of two vectors using vector addition. And here's what I mean by that. We could say that vector v is equal to vector v1, 0 plus vector 0, v2, right? If we add these two vectors together, we add the x components and the y components, v1 plus 0 is just v1, and 0 plus v2 is just v2. So added together, we would have v1, v2. All right, this is still the same vector we had before. But now watch what happens if we were to pull out a scalar multiple from each of these vectors. In particular, we're going to pull out v1 from this vector and v2 from this vector. And here's what that looks like. This will be equal to v1 times a vector 1, 0 plus v2 times the vector 0, 1, right? We can do that because if you multiply these scalar multiples back through the vectors, v1 times 1 is v1, v1 times 0 is 0, v2 times 0 is 0, and v2 times 1 is v2. So by pulling out those scalar multiples, notice what we have here. We have a scalar of v1 times a position vector of the point 1, 0, plus another scalar multiple times another position vector of the point 0, 1. Do these two position vectors, or more specifically, these two unit vectors, look familiar? Well, they're actually the standard unit vectors we just looked at. This vector of the point 1, 0 is the same as vector I, our standard unit vector for the x direction, and this position vector of the point 0, 1 is the standard unit vector j for the y direction. So we could rewrite vector v to be equal to v1 times I plus v2 times j. And this is another way to represent the same vector. Vector v would be equal to this vector right here, the position vector of the point v1, v2, but we could also write it like this, by breaking it up into its x component and its y component multiplied by the appropriate standard unit vectors. Right? v1 is the x component of vector v, and we're multiplying it by the standard unit vector for the x direction. And then we're adding that to the y component of vector v, and we're multiplying that by the standard unit vector for the y direction. And so we have the same vector, but just a different way to write it or define it. Okay, but now let's look at an example where we actually work with some specific vectors. Here we have three vectors, vector v, vector w, and vector a, and what I want to show you with these three vectors is how we can rewrite them or redefine them using our standard unit vectors, vector I and vector j. And by the way, what we're actually doing here is what is called expressing our vectors as a linear combination of unit vectors. Okay, but here's what that looks like. Vector v will be equal to its x component of 2, so we'll have 2 times the standard unit vector for the x direction, which is vector I, and then we're going to add that, or in this case, I guess we should subtract because we have a negative y component, so I'm going to erase that plus sign. We will subtract 3 multiplied by the standard unit vector for the y direction, which is j. And so this right here is the same vector that is expressed right here, but it's written in a different way. All right, this is vector v expressed as a linear combination of unit vectors. Now let's do the same thing for vector w. Vector w will be equal to its x component of 6 multiplied by the standard unit vector in the x direction, which is vector I, and then we'll add that, or in this case, once again, we have a negative y component, so we will subtract it. We'll have minus 9 times the standard unit vector in the y direction. And so that is vector j. All right, so once again, same vector that we have right here, but now we have expressed it in a different way. It is expressed as a linear combination of unit vectors. All right, now one more time, let's do the same thing for vector a. Vector a will be equal to its x component of negative 2/3 times the standard unit vector in the x direction, which is I, and then we will add that to the y component, which is just 1. So we're going to have 1 times the standard unit vector in the y direction, which is j, so we'll have j times 1, which is just j. All right, so we don't need to write that 1. Just like when we work with variables in algebra, we don't typically write 1x, we just write x, and it's assumed that the coefficient is 1. We do the same thing for these standard unit vectors. Okay, but there we have it. That's vector A expressed as a linear combination of unit vectors. It's the same vector that's up here, but just written in a different way. All right, and when these vectors are in this form, you can easily find the slope of these vectors. I guess you could do this before as well in this other notation up here, but all you have to do to find the slope when they're in this form is take the y component, or the coefficient of j, and divide it by the coefficient of I. All right, in other words, we're taking the y value and dividing it by the x value, because slope is rise over run. How far you move in the y direction divided by how far you move in the x direction. So the slope for v would be equal to negative 3 divided by 2. The slope for w would be equal to negative 9 divided by 6, which we can simplify to be negative 3/2, right? Negative 9 and 6 are both divisible by 3, so we have negative 3/2. And the slope of a would be 1 divided by negative 2/3, right? 1 is the coefficient of j divided by negative 2/3, the coefficient of I. And 1 divided by a fraction will just be equal to the reciprocal of that fraction. So the slope is equal to negative 3/2. And so now that we have found the slope of each of these vectors, I want you to notice that we have the same slope for all three of them. And so what that tells us is that all three of these vectors are parallel. They all have the same slope, so they're all pointing in the same direction. They are parallel vectors. And since they're parallel vectors, remember from a previous lesson that parallel vectors are actually just scalar multiples of the same vector. So what we should be able to do here is rewrite vector w and vector a to look like vector v, but multiplied by a scalar multiple. And so here's what I mean by that. Notice that we can pull out a common factor of 3 from 6 and negative 9 in vector w. So vector w could also be expressed as 3 times the vector of 2 comma negative 3, right? 3 times 2 is 6, 3 times negative 3 is negative 9. So we just have 3 times the vector, which is vector v. All right, so w is just 3 times vector v. And then for vector a, we can pull out a factor of negative 1/3, right? If we pull out negative 1/3, we'll be left with 2 comma negative 3. All right, negative 1/3 times 2 is negative 2/3, and negative 1/3 times negative 3. The negatives cancel out, and 3 divided by 3 is just 1. So a is negative 1/3 times the vector, which is vector v. So we could say that vector a is also equal to negative 1/3 times vector v. All right, now why did I point this out? Why is this important? Because now since we know that these three vectors are parallel, which then also means that they are all scalar multiples of the same vector, what we can conclude from this is that parallel vectors will also have the same unit vector. And so this goes back to the beginning of our lesson where we talked about finding a unit vector in the same direction as a position vector, right? If we wanted to find a unit vector in the same direction as vector v, we would just take vector v and divide it by its magnitude. What we're going to find if we did that for all three of these parallel vectors is that they're going to have the same unit vector. Because they're all just scalar multiples of the same vector, each of their magnitudes are just going to be the magnitude of v multiplied by that scalar multiple, and so if you divide those vectors by their magnitudes, you're just going to end up with this same unit vector. And so let me show you that that's true. If we look at the magnitude of vector v, that will be equal to the square root of the sum of the components of vector v squared, and so that will be 2 squared plus negative 3 squared, and that will be simplified to be 4 plus 9, right? 2 squared is 4, and negative 3 squared is positive 9. And 4 plus 9 is 13, so this will just become the square root of 13. So the magnitude of vector v, or the length of vector v, is the square root of 13. So the magnitude of vector w and vector a we can find really quickly, because since they are scalar multiples of vector v, their magnitudes will just be that scalar multiple multiplied by the magnitude of vector v. That's a formula that we looked at in a previous lesson. So the magnitude of vector w will be equal to 3 times the magnitude of vector v, which is the square root of 13. So we have 3 square roots of 13. And if you don't believe me that that's true, you could go ahead and just calculate the magnitude of vector w as it stands, and you would find the same answer if you simplified it. But then for the magnitude of vector a, that will be equal to negative 1/3, that scalar multiple multiplied by the magnitude of vector v, which is still the square root of 13. So we'll multiply that negative 1/3 by the square root of 13. All right, so those are the magnitudes of our three vectors. And so if we were to divide each of those vectors by those magnitudes, we would get the same exact unit vector. All right, so the unit vector corresponding to vector v, we would find that by taking vector v and dividing it by its magnitude, which is the square root of 13, which would be equal to 1 divided by the square root of 13 times 2 comma negative 3. And that would give us 2 divided by the square root of 13 comma negative 3 divided by the square root of 13. And so that would be the unit vector. We will get this same unit vector if we went through this same process for vector w and vector a. Right? Because if vector w is just equal to 3 times vector v, if we divide this vector by this magnitude, those 3's will cancel out, and we'll just be dividing these two terms by the square root of 13. In the same way, vector a is equal to negative 1/3 times the vector, which is vector v, and so if we divide that by this magnitude, those negative 1/3's will cancel out, and we'll just be dividing both of these terms by the square root of 13. So we're going to end up with the same unit vector for all three of these parallel vectors. All right, so all of that to say this, when you have parallel vectors, they will have the same unit vector. If you find the unit vector in the same direction as one of them, you have the unit vector that is in the same direction of all of them. Okay, so that's a nice little fact that you want to keep in mind going forward. But now I want to look at one more thing that relates to our standard unit vectors. Hey there, real quick, before we get to the next part of this lesson, if you find my tutorial videos here at JK Math to be helpful and you want access to more content such as exclusive bonus videos and dark mode versions of my videos, I'd invite you to check out my membership site, JK Math Plus, where all of that content is available. To learn how to join and see a full list of everything you'd get access to as a member, you can head over to jkmathematics.com/plus. I'll have a link for that in the description of this video. Okay, so if you're interested in becoming a member, feel free to check that out. It's a great way to support me and the tutorials I make, as well as a great way for you to learn math better. But for now, let's get back to the lesson. All right, so the last thing I want to talk about in this lesson is how unit vectors and the unit circle are related, or how we can use unit vectors and a unit circle to come up with another way that we can define vectors. And so here's what I mean by that. If you take a look at this graph here, you can see that we have our unit circle, which if you're not familiar with the unit circle, all it is a circle centered at the origin with a radius of 1. So any line that you draw from the origin to the circle will have a length of 1. So we call this the unit circle. Okay, and you'll see that in this graph, I have our standard unit vectors drawn here. We have our standard unit vector in the x direction, which is vector I, and our standard unit vector in the y direction, which is vector j. And then in addition to those vectors, I also have a general unit vector u. All right, so this vector right here is a unit vector. It has a length of 1. All right, it reaches out to the unit circle. All right, now using what we know about the unit circle, we can define this unit vector u in a different way. If we draw an imaginary line here from where the unit vector touches the unit circle, and we draw that line perpendicular to the x-axis, so this is a right angle right there, and we label this angle right here, the angle from the x-axis to our unit vector u, if we label that with an angle theta, what we can do is use what we know about our trig functions to represent the x and y components of this unit vector. All right, so here's what I mean by that. If we want to define this vector u, that's going to be equal to some x component multiplied by the standard unit vector for the x direction, and then we'll be adding that to some y component multiplied by the standard unit vector in the y direction. But what are those coefficients of those standard unit vectors going to be? What are those x and y components? Well, the x component is just going to be the distance from the origin to that imaginary line, right? What is this x value right here that the unit vector u reaches out to? Well, this side of our triangle we could find using cosine, right? If you remember your trigonometry, you probably learned the phrase SOHCAHTOA, and what this tells you is how to find the sine of an angle, the cosine of an angle, or the tangent of an angle for a triangle. Sine theta is equal to the opposite side divided by the hypotenuse. Cosine of the angle is equal to the adjacent side divided by the hypotenuse. And tangent of the angle is equal to the opposite side divided by the adjacent. We're not going to be worried about tangent in this case, but notice that if we use cosine, we could determine what the value of the adjacent side is, which would be this side right here. The adjacent side to the angle is this side because the longer side, of course, is the hypotenuse. And the hypotenuse is just the magnitude or the length of our unit vector u, right? So we know that that has a magnitude of 1. So if we want to figure out what the adjacent side is, we could write the following equation that cosine theta would be equal to the adjacent side divided by the hypotenuse, which is 1. So I'm just going to represent our adjacent side with u1, right? That would be u1, and then the opposite side or the y measurement would be u2. But anyway, we would have that adjacent side u1 divided by the hypotenuse, which is a measurement of 1. Our unit vector has a length of 1. But dividing anything by 1 doesn't change the value, so really what we have here is that cosine theta is equal to u1. Cosine theta represents this x value, or the x component of our unit vector. So cosine theta is the coefficient of vector I, or in other words, cosine theta is the x component of unit vector u. Now in the same way, if we want to find u2, or the y component of our unit vector, we can find that using sine. Sine of our angle is equal to the opposite side, which is u2, divided by the hypotenuse. So we'd have sine theta is equal to the opposite divided by the hypotenuse, so we'll have u2 divided by 1. All right, so I'll write u2 divided by 1, but once again, dividing a value by 1 doesn't change that value, so really we have that sine theta is equal to u2. And so u2, the y component of our unit vector u, is just sine theta. So we can write in sine theta as the coefficient of j, the standard unit vector in the y direction. Okay, so what we found here by using the unit circle and our trig functions is that we can represent a unit vector using its angle from the positive x-axis. All we have to do is take the cosine of that angle and then the sine of that angle. All right, and so these are the two ways that we could express that. You could use a linear combination of your standard unit vectors, or you could use this standard vector notation. Okay, and we can actually take this one step further. Remember from earlier in this lesson that we said that we can represent any position vector using its magnitude multiplied by a unit vector, right? We said that a position vector v would be equal to its magnitude multiplied by a unit vector in the same direction of vector v. And so using these definitions of that unit vector, we could also say that a position vector v would be equal to its magnitude multiplied by this unit vector of cosine theta comma sine theta, which would then also be equal to the magnitude of vector v times cosine theta times vector I plus the magnitude of vector v times sine theta times vector j. Right, we could rewrite this vector to be a linear combination of standard unit vectors and then distribute that magnitude of vector v to both of those terms. So we have the magnitude times cosine theta times vector I plus the magnitude times sine theta times vector j. Okay, so those are two nice little byproducts of being able to represent a unit vector using sine and cosine of the angle measured from the positive x-axis to that unit vector. All right, it's important to remember that that angle theta is a measurement from the positive x-axis to the unit vector. All right, you can't use any other angle to represent that unit vector. It has to be that specific angle. Okay, and so before we close this lesson, I want to show you one example of where these definitions are helpful. Okay, so here's our example. If the magnitude of vector v is equal to 3, and theta is equal to 30 degrees, or pi divided by 6 radians, with the positive x-axis, find vector v. Okay, so for this problem, we don't actually know what the components of vector v are, but we can find them using the known magnitude and angle that that vector is making with the positive x-axis. Or in other words, we can find a vector v using its magnitude and its direction, right? That is ultimately what this angle is giving us, the direction of our vector v. All right, so if we use that formula that we just found, we know that vector v will be equal to its magnitude multiplied by the unit vector in the same direction as vector v, but that unit vector can be represented by this vector, cosine theta comma sine theta, and we can rewrite that to look like this. We'll have the magnitude of vector v multiplied by each of these components, but then I'm going to rewrite them as a linear combination of our standard unit vectors. So we'll have cosine theta times vector I plus the magnitude of vector v times sine theta times vector j. Okay, so if we plug in our known values, and for the angle, I'm going to choose to use the angle in radians, not degrees. It's typically easier for us to work in radians, and so I'm going to choose to use pi divided by 6 instead of 30 degrees. So we'll have that this is equal to 3, right? That's the given magnitude of vector v, times cosine of pi divided by 6, and that's multiplied by vector I, and we'll add that to 3 times sine of pi divided by 6, and that is multiplied by vector j. Okay, now if we simplify, cosine of pi divided by 6 is the square root of 3 divided by 2. So this is equal to 3 times the square root of 3 divided by 2 times vector I, and that will be added to 3 times sine of pi divided by 6. And sine of pi divided by 6 is 1/2, so we have multiplied by 1/2, and that's multiplied by vector j. Okay, and now if we simplify one more time, this is equal to 3 square roots of 3 divided by 2 times vector I plus 3/2 times vector j. And so that is one way that we could represent this answer. This is vector v, that's what we wanted to find, but that's not the only way that we could represent it. We could also use our other vector notation and have that it's equal to 3 square roots of 3 divided by 2, comma, 3/2. All right, so either of those answers would be acceptable. Both of them are correct. They represent the same vector, just in different ways. Okay, and so that is the end of this introduction to unit vectors. If you want to see some more examples, feel free to check out my examples video that I'll have linked here on the screen. If you have any questions, feel free to leave those in the comments. But if you don't have any questions, this is all I had for now. So I'll see you next time.